All right, good morning, guys. I want to continue our lesson on confidence intervals. Today I'm going to be going over the second PowerPoint that I've given you guys. This one's going to be covering confidence intervals for proportions. So let me just write that out. It's confidence intervals for proportions. And so the last lesson was about confidence intervals for sample means. And now we're going to be looking at proportions. And we're still going to be looking at or using the same acronym, which is the following, right? PANIC. And I still want you to do the same things, right? State your parameters for the letter P. State your assumptions. Name the interval. Give me the calculation. So I consider, let me look for a color here. I consider step I. When you do this step, this is kind of like your calculation part. This is where you do all your calculations. And so some of you, when you turn in your assignment, you submitted just your calculations and your conclusions. But I also wanted you to state, your parameters, assumptions, and naming the interval. And so today I'm going to be going over, what are some changes that happen in the PANIC model for proportions. And there's a couple of changes we're going to go over. There's going to be a changing of the symbols. There's going to be changing of the assumptions. There's going to be also a slight change in the name and in the calculations, but the idea is the same. We're looking for a kind of a lower bound and upper bound. Okay. Now, to kind of start off, and I'll talk a little bit about this right now because I know that I gave you a file on Blackboard. And so on that file, I think I mentioned the assumptions, right? And so if you look at the following file, it's called acronyms. Let me check the name again. Yeah, I think I titled it acronyms for confidence intervals. But you'll see these two kind of yellow boxes, and we're going to be looking at the assumptions for proportions. And so there's three. There's making sure that the sample that you collected was random. Making sure that the 10% condition, that statement that you would write where you would say, it's safe to infer that there are at least these many items in the population to ensure independence. And so what's different here is to compare side by side the means and the proportions. What's different is actually step 3. Okay, for means, remember we were looking for if the sample size was 30 or greater, or if they gave us the data, we can graph it and check the shape to see if it's normal, or like in problem number 3 of the last assignment, they told us that the data was normal. So there's 3 ways to check for normality. Right? Check to see the sample size is 30 or greater. Check to see if they gave you the data so that you can graph it. And the third way is if they tell you that the data is normal, then we assume that the sample is going to be normal. Okay, but for proportions for today's lesson, there's a different check that we have to do. It's called the success and failure condition. And so what we're going to check for is our sample size times the proportion greater than or equal to 10? And is our sample size times 1 minus the proportion is greater than or equal to 10? So it's called success failure because if P is my probability of success, then 1 minus P is my probability of failure, right? So if I have, 70% chance of success, if my P is 0.3, let me write that out. Let me zoom in here. So it's called the success and failure condition because, for example, if my p-value is 70%, if this is my success rate, then what's my failure rate? What's my failure rate? 1 minus p. It would be 1 minus 0.70, which is 0.30. So I have my failure percentage and my success percentage, and I'm multiplying these two percentages times the sample size that I got. So I'm going to do n times p and n times 1 minus p to check if those two values are greater than or equal to 10. Okay. Now the next thing I want to talk about is how did the symbols change? Because if you remember the last lesson, we were working with means. So on step P for the parameter, you would say, P in the acronym, and you would say, the parameter is this symbol is the true mean NOx level, or the true mean temperature, or the true mean coffee score. Okay, and then what we would use in our calculation is the statistic. Okay, so we have the parameter and the statistic. Now that's for means, right? But remember, when we were doing sampling distributions, the last lesson before we went off to spring break, we talked about proportions, right? And there was a symbol change there also. And so now we're going to be saying, when we look at the parameter, we're going to be saying our parameter is P, which stands for the proportion. Remember the Reese's experiment? We checked to see what's the proportion of orange in a Reese's bag, and the Reese's company wanted that proportion to be 0.5, right? But everybody in the class got different cups, different samples, and so each person had a different p-hat. Each person had a different proportion of orange. Some had more than 50, some had less than 50, or some had exactly 50. But we graphed all these p-hats to check to see if it matched, or if the center was close to the Reese's parameter. Okay. So that's the changing in symbols. So we're going to use p and p-hat now. Okay. And then, let me see where I want to go to next. Okay, hold on here. All right, so the next thing I want to talk about is when we're working with the interval, right, we have to find the standard deviation. So that's also going to change. Okay, so it's going to change to the following. I'm going to change slides here, but it's going to undo my markings or my drawings there. All right, so the next slide that I want to talk about is this one, and it'll animate in the PowerPoint if you look at it. And so here we have the symbols, and we have also down here, if you remember from sampling distributions, you have your formula chart. And again, I think the formula chart is on Blackboard. I'll check. If it's not there, I'll upload it. But if you remember, the mean or the parameter was P, and this was the standard deviation. So in the confidence interval, we have to find the standard deviation. We have to use that to add and subtract, remember? We're going to add and subtract to find an upper and a lower bound. Okay? But we're going to use, instead of p, because this is what we're trying to estimate. We're trying to estimate the parameter. We're going to be using the symbol p hat, which I'll show you. I'll show you that in the next slide, and you'll see the changing there. But we're going to use p hat here. So in the next slide, what I want to point out is the formula. Okay, and so this was the formula we used for means. And you know, we would say this is a 90% interval, or we would say 80% interval, 70% interval. So this is part of the naming process. So in this part, this is the name that we would use when we're working with means. Okay, but for this lesson, this is the name we would use for proportions. Okay, and along with that name goes a formula. Notice the changes to the formula though. Instead of x bar, we're going to be using p hat. We still have plus and minus. We still have the z value. And look how the standard deviation changes. It changes from sigma over the square root of n. And that's going to change to the square root of p hat times 1 minus p hat over n. Okay? Now, the next thing I want to talk about is the conditions. Again, I just want to reiterate, because it's on the slides too, so I want to make sure that that I cover it. But the conditions, I just want to mention them again. We have to check, is the sample that you collected, was it random? Check for normality. This is kind of like the central limit theorem. But we're checking to see if it's greater than or equal to 10. This is called the success-failure condition. And then this is the 10% condition, where you say it's safe to infer that there are at least 10 times the sample size to ensure independence. So the first one and the last one are the same as the last lesson. Again, the only difference is how to check for normality, right? To check if it's normal. Also, again, the thing that applies here is if they give you the data. But for the most part, for proportions, they just give you the percentage. Okay. All right, so let's look at the example. So it says, in a study of airbag effectiveness, it was found that in 821 crashes of mid-sized cars equipped with airbags, 46 of the crashes resulted in the hospitalization of drivers. Okay? And it's asking us, give a 95% confidence interval for the percent of crashes resulting in hospitalization. Interpret the confidence interval. Okay, so this is problem number 1 in your second handout. And we're giving a 95% confidence interval, but for a percentage, right? Not a mean, a percentage, proportion. Okay, so we're still going to do panic. And so let's see what we're going to do in this case. And so in the PowerPoint, you'll notice a couple of things, right? This P here stands for parameter. Let me write it up here, parameter. So that's why I kind of color coded, because a lot of students get confused that I put P twice. Why did I put P twice? Well, 1P stands for parameter. 1P stands for the proportion. Which proportion? The true proportion of what? Of crashes. Okay, so the first P in panic stands for parameter. The second P stands for proportion. Okay. The other thing we have to figure out is in our sample, right? In a study, we sampled 821 crashes. Okay, but we were only interested in the crashes that resulted in hospitalization. So what percentage was that? Well, we would take 46 divided by the total number of crashes, and that would give us the percentage of crashes hospitalized. This is our sample percentage. Okay, and so I just kind of outline, what the PowerPoint is referring to. Now, step A, which stands for, assumptions. Here, we assume that they collected the number of crashes randomly, right? It doesn't say that it was a random collection, but we assume it is. And so I'm going to say that that's number 1 of our assumptions. Number 2, is 2 parts actually. Checking to see if these 2 are greater than 10. So I'm going to do n times p. Where did I get this p from? From the sample data. And I'm going to check to see, is that greater than 10? And you can calculate that on your own calculators. Check to see if it's 10, and I put a check mark there, right? All right, the next thing we have to calculate is n, which is 821, times 1 minus p. And this p again is from over here. So is this greater than or equal to 10? And I put a check mark because it is. Okay. If I get 2 check marks here, that means the sample size is large enough to use a normal distribution. That means we can use the normal table, and that's fine with me. Okay. And then assumption number 3. And notice that I'm not going in any particular order, right? These 3 assumptions, 1, 2, 3, we can go in any order. I just chose to go in this order to check off. Okay, and the reason we're checking these off is to make sure that we can use a normal distribution, to make sure that we can create a confidence interval that's going to be accurate. Okay, so let's look at assumption number 3. It's safe to infer that the population is at least 8,210 crashes for independence. Again, where did I get 8,210? Anybody remember? Where did I get this from? That's just taking, multiplying 10 times the sample size. Okay, what was the sample size? 821 times 10 is 8,210. Okay. All right, so that's P and A. Let's go on to N. Okay, so this is where I changed it, and if you look at the PowerPoint, there's an animation where I changed the name. Okay, let me go ahead and use kind of a whiteout to white this out really quick. So, okay. And I'm going to explain what I'm looking for here. Okay, so in the naming, remember the last lesson we would say, oh, it's a 95% confidence interval, right? Now, what I'm going to look for is the name of the interval as far as what are you working with? Are you working with a proportion or a mean? Because now I introduced another category, right? Is it a proportion or a mean that we're working with? So now I want you to identify that. I want you to identify what am I working with? So in this case, I'm dealing with one proportion z interval. One proportion z interval. Okay? One proportion z interval. So I'm working with one proportion z interval. Now, the reason I'm changing the name also is because, and I'm going to pull up an image here. I just took a screenshot of my calculator, and in the calculator, I don't know if you can see this. I think you can, but in the calculator, when you go to menu and you go to statistics and you go to confidence intervals, it's going to have a list of names. Okay, and so notice that it doesn't say 95%, 90%, 80%. It's asking for a type of interval, right? So we're going to be, last class we were looking at z intervals. This lesson we're looking at one proportion z interval. And in the next lesson I'm going to talk about t interval and then two sample intervals. Okay. Okay, so let me go ahead and delete this. All right. Now, step I is the calculation part. Remember, I named it the calculation part. Now, instead of x bar, we're using p hat. We're still using z, and then we're using p hat and p hat here. Now, the reason it's called z because we're using the normal table. And how do we know that we can use a normal table? Because our sample size was greater than, I'm sorry, not because our sample size was greater, because when we calculated n times p and n times 1 minus p, we got greater than or equal to 10. Okay, so I'm going to substitute, what's my p hat? It's 0.056, so I'm going to put that here. Plus or minus, what's the z value for 95%? What is the z value for 95%? So remember how we did this last time? We look for, what's 100 minus 95? That's 5%. What's half of 5%? 0.025. And we would look at 0.025 in the table, and that should give us 1.96. Okay, that hasn't changed. Next step, substitute, right? We have square root. P hat is 0.056 times 1 minus p hat divided by n. Okay, we calculate this. Remember, we're going to do two calculations, adding and subtracting. And we get a lower bound and an upper bound. Okay, so our conclusion statement is we are 95% confident that the true proportion of crashes lies between 0.0403 and 0.0718. Okay, and a little note that I put there at the bottom is, since we had to assume that the crashes were a random sample, there might be inaccuracies in our conclusion. Okay, that's just a side note that I wanted to mention there. Okay, because if you look at the problem, it doesn't mention anything that the sample that was collected was random, so we run the risk of inaccuracy. But this is the procedure. Again, it's similar, right? Instead of saying true mean, we're saying true proportion. the bottom here, right? See this? So there's not much changes, just little symbol changes here, one change in the assumptions, and a name change. Okay, but the same idea. And then the last thing I want to discuss is part B of number 1, which is, again, quite similar to the last one, to the last lesson. Right? It's asking for how large of a sample would be needed to obtain the same margin of error as in part A for a 99% confidence interval. So notice that the interval changed. Notice that we're using the same margin of error as part A. Okay. What was the margin of error for part A? Well, there's two ways to calculate it. I put one there on the PowerPoint. Okay. But the other way to calculate the margin of error is to look at the previous part. Look at part A. What did we have for part A? What did we have for part A as far as after the plus and the minus? And I'm trying to decide what color to pick. Okay, so for part A, and I'm going to do this on this side here. For part A, we have the following formula, right? Okay, we have the following formula. And then we substituted. But this value here is going to be this value here. And you can calculate it. This is from part A. Okay. Calculate this for me and check to see if it's the same as this. And so if it is, that's what we're going to use for the margin of error. Okay, that's what we're going to use for the margin of error, which I put over here. Now, also please make sure to look at the PowerPoint because the PowerPoint kind of animates everything. Okay. And the other thing I want to mention is where did I get the 0.25? Where did I get the 2.576? So in part A, remember, the confidence percentage was 95%. This is for part A. Remember, it was a 95% interval that we got the z value for. But what is it asking for in part B? It's a 99%. So that's going to give me a different z value. Okay. P hat stays the same. This is the margin of error. It has to be less than that margin of error. And then we're looking for sample size, so I left n as a symbol, right? So you divide 2.576 on both sides. When you divide, you get 0.0061. I went ahead and multiplied 0.056 and 1 minus 0.056, and it gives you this. And then to get rid of the square root, we square both sides. When you square this side, it gives you this. Then we can cross multiply. You can cross multiply, or you can multiply by n and then divide by 0.000033729. But our conclusion is going to be we need a sample size of at least 1,419 crashes. Okay. Now, if you have more questions concerning this, feel free to email me or communicate with me on Remind. And I just hope you have a great rest of your day, and stay safe and cautious and protect yourselves. Until next time, have a great day.